Hello everyone, my name is Charity. I am a student teacher here at the University of British Columbia, and this is part 2 of my organic chemistry series made by our teachers here at UBC Impact and made for our VAS lab sessions at the lift solder session, at the lift solder building. All right, so today we will be learning about continuing our session on organic chemistry. So last time we did alkanes. So what we did was we looked at all the things that you guys need to know for KCSE about alkanes. So you guys should be able to remember all of this. Something I want to point out and review before we start is just alkanes and physical properties. So it's really important to know these physical properties, not because I want you to memorize them, but because I want you to know the difference between methane and decane. And the reason why, if you understand the difference between methane and decane, you will be able to figure out what each of these physical properties, the differences in their physical properties, because you know the difference between methane and decane is the number of carbons on their carbon chain. So what that number of carbons is you increase the number of carbons on the carbon chains, that changes things about the molecule and actually makes it easier or harder for these physical properties to show up, and easier and harder for these molecules to interact with each other. So again, we are looking at the intermolecular forces. We are looking at one methane molecule compared to another methane molecule. How are they going to interact? When they come together, are they going to stick together, or are they more likely to just move past each other? And then we have, again, one decane molecule and another decane molecule. When they come together, are they going to stick together, or are they going to go apart? And we know that because decane is a longer molecule, it has more carbons, it has more hydrogens, it's going to more likely stick and attract to each other because they've got more electrons floating around them. So it's going to make them stick together easier. And so if things stick together easier, that means that it's going to be harder for them to move around each other. So it's also because they are bigger, it's going to be harder for them to move around each other. And when we look at melting and boiling point, when we're talking about melting and boiling points, we are talking about the states of matter. We are talking whether they are a solid, whether they are a liquid, and whether they are a gas. So when we look at methane, methane is really easy to be in a gas form. You can see this already. When you have methane in room temperature, you should know methane at room temperature, at normal temperature, it is a gas. And this is why methane only has one carbon. So one carbon, it's going to be really easy for them to move around each other. But then you look at things like decane, where it's 10 carbons, right? So 1, 2, 3, 4, 5. That's going to be a very long chain. And that's why your decane molecule will move around each other slower. And so you can immediately know that, well, we know that our melting point for methane is very, very low, which means that it becomes a liquid at a very low temperature. It boils at a very low temperature. And what does that mean? Pause the video right now and think about to yourself, what does it mean to boil at a very low temperature? Okay, I'm pausing the video right now. To boil at a very low temperature means that it is usually in a gas state, right? Because if you boil at 0 degrees Celsius, that means it's almost like normal humans live in 20 degrees Celsius. So then almost all the time it's gas, right? So that means the boiling point is very, very low. And as you have longer and longer carbon chains, it's harder and harder for them to move around each other. And so they kind of get stuck together, right? It becomes very hard for a decane molecule to move around each other, because what a decane molecule is, it's not just one carbon, it's 10 carbons. Then we look at viscosity. Again, viscosity is the property of when they are in liquid form or when they are in fluid form. How easy is it to flow? The speed of it to flow. And that, again, very similar. When you have two decane molecules, they're not going to move around each other very fast. They're going to have all the little carbons and hydrogens, they're going to be making and interacting with each other and attracting each other. But in methane, that's just one carbon. So it's going to move very fast around each other. So again, the same logic. I'm going to skip flammability right now. We're going to come back to it. We're going to talk about density. So again, density is about how it floats in compared to other fluids. And obviously we can see that the more dense an object is, something for an object to be more dense than another object, it means it's heavier than another object in fluids. So we can see immediately, it's very obvious that decane is going to be more dense than methane because decane has 10 carbons while methane only has 1. Again, same thing, solubility in water. Like when you're in water, you want to be dissolved in water. You're going to have this methane molecule in the water. It's going to be interacting with all the other molecules. It's going to mix together. And obviously, because methane is smaller, it's going to be able to dissolve faster. Something to note that all alkanes are not supposed to be soluble in water. So you can see right up here that alkanes are non-polar. And so that means because water is polar, it will not dissolve in water. However, if the question asks you, is methane more soluble in water or is decane more soluble in water? Methane is more soluble because it is smaller. However, if the question asks you, are alkanes soluble in water? The answer is almost 99% of the time no, because what an alkane property is, alkane properties are non-polar. And for water, water is polar. So these two do not mix, right? Polar will mix with polar, non-polar will mix with non-polar, but it's very difficult for non-polar to mix with polar. So that's something you want to keep in mind. Okay. So we have all these other things. We have lowest temperature to highest temperature, least viscous to most viscous, most flammable to least flammable, least dense to most dense, and most soluble to least soluble. And then we will see these methane, ethane, and propane and butane are usually a gas at room temperature. And then pentane, hexane, heptane, octane, nonane, and decane, these are usually going to be liquid at room temperature. And that's, you don't have to know the ones more than 11 carbons, but just know that this trend will continue for 11 carbons, 12 carbons, 100 carbons, right? As you increase the carbon chains, their melting point will get higher. The viscosity will be stronger. The flammability will get lower. And all these trends will continue, assuming there's no other difference between the length of the carbon chain. So next we want to talk about a visual representation of solubility and density. And so here you see that your liquids, these are oils, so these are most likely going to be non-polar. So you can see immediately that these are oils, like alkanes, are going to be a lot less dense, and they're going to be floating at the top. They're going to be very separate. However, when we talk about methane and ethane and propane and butane, they're gases. So when we talk about them being soluble in water, they're not liquid. So you can't see them in this sense because they're gas. They're going to be floating in the air. You can't trap them there. But you can mix the air into the water, but it will not look like liquid. That's something to keep in mind. Yeah, it just to explain to you that when we talk about like solubility of methane and these gases in water, it's like actually they're gas bubbles in water. It's not liquid in water, right? So this is the things you need to know for alkanes. And something you'll notice that we didn't cover, actually, we didn't cover isomerism. So what is isomerism? We're kind of going to go over that today, right now. So first, this is IUPAC naming. So this is how like the world and the scientists decide to name chemicals, because you have names like butane, methane. And so who came up with them, right? Like who came up with them? And so this is who came up with them. IUPAC naming. Methane is an IUPAC name. So IUPAC stands for International Union of Pure and Applied Chemistry, and basically they are comprised of a bunch of scientists who came up with a set of rules to name these chemicals. And so why would we name these chemicals, right? So we would name them because we have so many ways to look at chemicals, right? Because really at the end of it, when we look at a chemical, we have 4 carbons and 10 hydrogens, right? But then we look at another molecule. This also has 4 carbons and 10 hydrogens. But when you look at these 2 molecules, you can tell that they are different, right? One of them, all the carbons are in a line, a very straight line. The other one, the carbons are not in a straight line, and you can't turn this carbon into a straight line. So these are 2 different molecules. They are covalently bonded differently. And so how are you going to tell the difference between butane and isobutane? Isobutane is not an IUPAC. So you're going to be able to tell the difference not by counting the number of carbons, because as you can see, they all have the same amount of carbons. So before we talk about sort of how we're going to name them, I want you guys to pause the video now and explain to you why these guys are not the same. Obviously, I explained it to you earlier that it's not in a straight line, and this is not in a straight line, but why can't you just, turn the carbon and move it to the other side? Why can't you do that? Unpausing the video right now, you cannot turn isobutane into butane because when you look at this line here, this bond here, this bond is a covalent bond. You don't break covalent bonds that easily, right? If this, for example, you have two butane, these two molecules are in like the air, and you have like an intermolecular force. This is a London dispersion force, an intermolecular force. This thing can be broken at any time. But when you have a bond like this is a covalent bond. You do not break covalent bonds easily. They are very hard to break. So, because they are the bonds that make a molecule. Whereas this bond, this is called an intermolecular bond. Intermolecular bond. And this one would be an intramolecular bond. So these bonds are not bonds you can break very easily. So you cannot turn this molecule into this molecule. Okay, excellent. Can you see my screen here? So when we can look at some examples here. So why are these methane and ethane, the propane, the same? So when let's just look at this methane molecule. We can see that it has 1 carbon and 4 hydrogen. And the reason why these two are the same, even though they're technically different, right? They don't look the same, right? This one has the hydrogens placed diagonally, and this one has them placed horizontally and vertically. But you can turn the molecule, right? If you turn this molecule, you move it over on the piece of paper, you can easily turn it into this molecule. And the same goes for these molecules. Let's look at ethane now. So you have 2 carbons, and then all you do is you turn it over. These two can be easily turned over. So this is the same molecule. These two blue molecules, ethane molecules, they're the exact same. And the reason is all you need to do is you turn them over. Let's look at propane. So this is propane, right? So you can count 1 carbon, 2 carbons, 3 carbons, that's propane. 1 carbon, 2 carbons, 3 carbons, that's propane. 1 carbon, 2 carbons, 3 carbons, there's propane. So these are all propane molecules, and these are all the same propane molecules. And why is that? When we look at this, look at the carbon backbone. That is the most important thing you want to be looking at. You're looking at the carbon backbone. This carbon backbone never breaks. It's always 3 in a row. 3 in a row. 3 in a row. This is weird. This is a very strange carbon backbone. But what it is, the carbon backbone never breaks. But then let's compare it. Now let's compare it to our butane molecule. Okay? So let's look at the carbon backbone. So here the carbon backbone never breaks. But then when we look at here, carbon backbone, you take a 1 line and you try to draw the carbon backbone. You can't go back here. You cannot. You have to go back to a previous carbon and then go down. Whereas for this one, all you need to do, you start from any carbon, you continue to the very end. You start from any carbon, you continue to the very end, and you've missed a carbon, right? So you cannot turn this molecule into this molecule. These are 2 very different molecules. They are not the same molecules. For all of the other ones, methane, ethane, and propane, these guys, you can turn them, you can twist them around, you can turn them into the same molecule. They are the same molecules. They are the same formation. So we will have a YouTube video right here. So you can see here that this person has brought out an ethane molecule. So the black balls, these ones, they are carbon molecules. And you can see the white balls, these are hydrogen molecules. So what they're going to show you is that you can turn ethene. Okay, excellent. So that was ethene. And now we're going to be looking at sort of branching. So the difference that you guys see here is that actually there's one carbon chain, but then suddenly there's this other thing. There's this new thing that pokes out from the carbon chain. It's not part of the carbon chain, which is our single line, right? We can draw this in one line. We have this new isobutane. In isobutane, we have this thing that pokes out, and that is a branch, right? We're going to talk about branch. So isobutane is not the IUPAC name. We're going to name it this molecule in IUPAC. Because this is butane. Everyone knows this is butane, but this is something else. So we're going to look at this. We are going to learn about IUPAC naming. So we have this example that I want you guys to know, and we're going to be looking at this example for when we learn how to name things. So first, we have the first part of this is so the thing in red. This is an IUPAC name. So right. So over here you can see, hey, this looks like butane, right? It looks like butane. And so that is what's going to tell you what is a carbon chain. That's going to tell you the number of carbons it has in that one straight line. But then you have a branch, right? Okay, so this part, the front part is going to tell you what branches are there. And then at the very end, you're going to have things that tell you special things about the hydrocarbon, right? So here, this is methylbutane. So we can see here that it is butane because we have what? 1, 2, 3, 4. 4 carbons on the backbone, right? We can draw these 4 carbons, we can circle them in one straight line without taking it off. But if we try to take this one, then we leave out this one. So if we try to take this carbon, then we leave out this one. So clearly this is not part of the backbone, or this one, right? It doesn't matter. Either of them is not part of the backbone, whichever backbone you want to take. So let's just say these 4 are a backbone. Then we have the branches. So this is the special part. On the 3rd carbon, we can see that we have a methyl. And why is it a methyl? Remember, methane has 1 carbon, and so a methyl branch has 1 carbon. So that is 1 carbon that goes off the main carbon chain, right? So that is a branch of the main carbon chain. And then at the end, you have a very special thing. You have an OH group, and OH groups are very special, so we give them an OL name. So that's important for us to know because these are special groups that are going to tell us atoms that are not carbon or hydrogen that are going to be on our atom, a molecule. So here, right here, that if I did not draw the hydrogens, but if we drew the hydrogens, this is what it would look like. And a lot of times they will simplify, the hydrogens will fill up every other place that the carbon is not attached to because carbons have 4 valence electrons. They want to be filled with an octet, so they will have 4 other bonds. Excellent. So now we will look at alkanes. And then we have alkenes. And then we have alkynes. So if you guys have seen this, great. If you guys haven't, then we'll learn about this later. So you notice immediately that you cannot have methane and you cannot have methine. That is very important because you will learn why later on. But you notice right here that you have the A, you have the E, and you have the Y. So then you look down and then you will see that all the atoms here, or all the molecules here have an A, right? And then all the molecules here have an E. And then all the molecules here have a Y. And so these 3 types of hydrocarbon backbones, an alkane backbone, an alkene backbone, or an alkyne backbone, they are going to tell you the carbon chain. So at the very end, the ENE or the ANE or the YNE, that is going to tell you what the carbon chain looks like. And at the front of it, at the front of this thing, at the front of it, you will see that you have these alkyl branches. And these alkyl branches are very similar in the sense that, yes, you will have the AN, and then you'll have the alkyl part. But you have the ENE or the ANE or the YNE, and then you have the alkyl branches, which has the YL, right? So that's what's going to be different from the backbone versus the branches, because the alkyl branches, they're both alk, right? You have the alkane, alkene, alkyne, but that's what's changing. What is changing is the thing at the end, right? You have alk, ANE, alkenes, alkynes, and then you have here alkyl. And so these are your branches. You have ethyl branch, a propyl branch, and methyl branch. But what's the same at the front? The thing at the front is all the same. The eth, prop, meth, that is all the same, right? You look here, eth, meth, eth, propyl, butyl, pent, hex, hept, oct, non, dec. That is the same between these two things, right? So your carbon backbone and your branches, they have the same starting prefix, right? Meth, eth, prop, but. What is different? It is the ENE, the YL, the ANE, the YNE, right? So that's what's different and what's the same. So you look at IUPAC naming again. Let me move my camera. So you have the branching and then the carbon chain. And then what's at the front, the same thing, everything at the front for the branching of the alkyl branches and the carbon chain branches, they're going to be meth, eth, prop, but, pent, hex, hept, oct, non, dec, right? So pause the video right now and please name this molecule. You've already seen this molecule. Unpausing the video, you can see that immediately. The carbon back chain is 4. We start with the carbon backbone, right? So we have 4. And then we know because it is a carbon chain, it is not a branch, it is ANE because it's an alkane. Then we count, there's 4, so it must be the 4th. It must be butane, butane. Then we look at the branch. You can see here that, well, look, this is the first carbon, this is the second carbon. So our branch comes off at this point. And then what is this branch? This branch is a meth branch. It only has 1 carbon. So then we will add methyl, right? So 2-methylbutane, this is our final name, the IUPAC name. So you notice that we've numbered the carbon. So we go 1, 2, 3, 4. So now, earlier, actually, we numbered it from 1, 2, 3. And then we had a branch starting from 3. But this time, we numbered it starting from 2. And so I'm wondering, why did we do that? Why did we start with 2 and not 3? The answer is, well, because we started with 2, it is a smaller number. And so IUPAC, because we want to favor things, we want to make things simple. Because otherwise, if we write 3-methylbutane or 2-methylbutane, that's very complicated, right? That's 2 names for 1 molecule. We want to keep it simple. We want each molecule to only have 1 name. We're going to choose the smaller number. Why? So why did we choose the 3-methyl earlier? Well, that's for a different reason, and we will get into that reason. But you usually want to choose the smallest number because it will help you determine, it will just make naming easier, and it will also communicate to other people and to your teachers and to other scientists what your molecule is. So we're going to do some practice questions. We're going to do a branching example. First, we're going to ask you, what is this molecule named? Pause the video right now and answer the question. Unpausing the video right now, the molecule is named octane. This is why, because we have 1, 2, 3, 4, 5, 6, 7, 8. 8 carbons in the carbon backbone. And we can, if we wanted, we can draw 1 single line throughout the backbone. So there are no branches, no branching. So then the second question is, what happens if you add a methyl group under this arrow? What is the name then? Please draw it out and please determine whether this answer is correct. Unpausing the video right now, we will see we have a methyl group drawn here. And then we have two different types of numbering. So we can either make it 4-methyl-octane, or if we count from this side, we can make it 5-methyl-octane. Please pause the video right now and explain why it's 4 or 5 to your neighbor. Unpausing the video right now, we will continue to name it 4-methyl-octane, and the reason is because we want the smallest number. There are no other special things happening with this octane. This is just a regular octane, so we're going to choose the smaller number. The answer of what this molecule is named right now is 4-methyl-octane. 4-methyl-octane. Then we have another question. Why is this not called 2-propylhexane? See, if we started from, let's look, we can technically have a carbon chain that is 6 carbons long, and then we have a 3-carbon long branch. So why is this not 2-propylhexane? Please pause the video right now and try it out yourself. I'm pausing the video. Well, the reason is because octane is actually longer than hexane. Octane has 8 carbons in the backbone. Hexane, we only have 6. And so to make it easy, when we choose the carbon backbone, we are going to choose the longest carbon backbone. Why? Well, because choosing the longest carbon backbone will give us the easiest sort of like naming system. If we choose the longest backbone, we will also usually have less complicated and long branches. So we want to always pick the longest carbon chain. And then for the numbering of the carbon chain, we want to pick the shortest numbering, the smallest numbering for the branches. Longest carbon chain, smallest, the number and the side that you number is, you want to number it from the side that will give your branches the smallest number. So another question. So we have octane again. What is the molecule if you add an ethyl? So what is ethyl? Ethyl group. We see the YL. First, the easiest thing to look at ethyl is we see the ETH. That is 2 carbons. We already know 2 carbons, right? ETH, that is 2 carbons. But then we see the YL. And what is the YL? That is an alkyl group. An alkyl group. So an alkyl group is a branch. So we're going to add an ethyl branch on this side. Please pause the video right now. Draw that molecule and name it. Unpausing the video right now, we can see that this is called 3-ethyl-octane, right? So we're going to choose the longest carbon branch, which is going to be octane. And then we're going to add we're choosing the numbering that's going to give us the shortest number, which is 3. Then I will have another question. What is this molecule name if you add a propyl branch? What is a propyl branch? Prop stands for 3, right? So we're going to have 3 carbons. And a YL, a propyl branch, that is an alkyl branch. Please pause the video right now, draw the molecule, and name it. Unpausing the video right now, we can see we have our propyl, sorry, not propyl. This should be ethyl branch. We're going to name it ethyl. Ethyl. This is, sorry. This is going to be, or I can, I will pause the video right now and change the answer so it'll be the same as what you. An ethyl branch under this arrow. And the answer is going to be, it's going to be decane. So why is it not 1-ethyl-octane, right? So why did we make it part of the carbon branch and not a branch itself? We made it part of the carbon backbone because, again, when we look at, let's start from 1 carbon. We draw all the way to the end. We can draw it in one continuous line, right? That means it's going to be part of the backbone. So the reason why I changed it to ethyl, again, you guys might have noticed, is because you guys don't have to learn about 11 carbons. So all you need to know is 10 carbons on a carbon backbone, right? So if I made it a propyl branch, right, then it would have been 11 carbons in the backbone, and you guys don't have to know that one. That's the reason. Then we have another question. So what is this one. So we have 3-ethyl-octane. We're going to look back at this again. So this is 3-ethyl-octane. What if we made it, instead of an ethyl-octane, what if we made it a propyl? Instead of an ethene branch, we made it a propyl branch. How does that change it? So I'm going to tell you the answer right now, but you guys should pause the video and try it out. All right, so I'm pausing the video right now. We're going to look, how does an ethyl octane change if you added a carbon onto that end of that branch? It actually changes it. It becomes 3-ethyl nonane. So you went from 3-ethyl octane, this is 3-ethyl octane, to 3-ethyl nonane. So notice that we didn't do 3-propyl octane, right? So why didn't we do that? Again, it's the longest carbon chain. The longest carbon chain is this one now, because it has 1, 2, 3, 4, 5, 6, 7, 8, 9. It is no longer octane. And you notice that if we go back, right, this is our octane branch. This one is correct, right? This is not nonane, because 1, 2, 3, 4, 5, 6, 7, 8, that's your carbon chain we've been counting. But if you went and counted this side, this is also 8 carbons. So you notice at this crucial point, at this carbon, when it splits off into these two smaller branches, it splits off into 2 carbons, and it also splits off into 2 carbons. So it doesn't matter which backbone you choose. You can choose this backbone. You can choose this backbone, right? It doesn't matter. As long as you don't choose this backbone, because this is obviously a very small backbone. It doesn't matter which backbone you choose. They're all going to give you 8. But as soon as we added, right, a carbon to this side, this is now 9 backbones. You are now forced to choose this one because this is the longest carbon chain, and then this will be your small branch at the side. This is 9 carbon. So it would be wrong to call it 3-propyl nonane, 3-propyl octane, whatever. Yeah. And you have another question. What do you name this molecule? You have 2 options. Please pause the video right now and choose it. Unpausing the video right now, we are choosing, I'm going to walk you through the answer about which one we chose. So we can notice right here that immediately, it doesn't matter which numbering side we start off with, right? Because they're all going to end up at 3. It's just that they're going to be different molecules or different branches that end up at 3. In this case, we're going to be talking about numbering alkanes. First, we're going to think about the functional group, right? So this is like, remember, we talked about that OL, that OH group with the special thing, right? You guys haven't seen any functional groups. I haven't given you any examples for you guys to try out yet, but the functional group must have the lowest number, but that isn't relevant here. There's no functional group, right? Then you take alphabetical order. So after looking at it, right, we want the alphabetical order, so that is ethyl. So E is higher in the alphabet than M. So the answer is ethyl, 3-ethyl. So this is the answer. Check. So this one is correct, and this one is wrong. Okay. It's 3-ethyl because it's alphabetical order, because we've already seen they're the same, right? There will be the same numbers, right? 3 and 3. What about this one? These are not the same numbers. What are you going to choose for this one? Unpausing the video right now, we are going to choose this one. So why did we choose this one? I thought it was alphabetical order. No. Okay, understandably, you're looking at the alphabetical order. But before you look at the alphabetical order, what are you looking at? Any substituent present must have the lowest possible number. That means any branch present must have the lowest possible number. Over here, what are your lowest possible numbers? You have 4 or you have 3. Which one is the lowest possible number? It is 3. Okay? So in this sense, when you have 4 and you have 3, these are 2 different things, right? But earlier, when we were looking at this is 3. This is 3. They're both the same. So then you look at alphabets, okay? Because alphabets don't tell you very much. It's not useful, right? But over here, this is useful because 3 or 4, because the numbers are different. So over here, here's your answer. And so then why did we write it like, why did we put ethyl in front of methyl? Shouldn't we have, or for in the correct answer, why did we do 5-ethyl? Why didn't we 3-methyl, 5-ethyl octane? And the reason is because, again, it's for naming simplicity. We want the easiest name to start. So we just name our branches in alphabetical order, but we want the lowest branch number. Again, we have this molecule. So we're going to look at this molecule. So please name this molecule. I'm pausing the video now. This molecule named is 3,5-dimethyl-octane. And we notice that because we have two of the same branches, we have two methyl branches. What we actually do, we don't do 3-methyl, 5-methyl, because that just takes more time to write out. What we can do is we add this di. So we tell the reader or whoever we're trying to speak to that this has two methyl branches. So we have 3 and 5-dimethyl. So it has a methyl branch at the 3rd carbon and has a methyl branch at the 5th carbon. And we can see right here that, yeah, this is what we have. We have it on the 3rd carbon and we have it on the 5th carbon. And we can see if we count it from the other way, you would have it starting from the 4th carbon and then the 6th carbon. So that is a higher number. So we want to keep the lower number. So that's why we're doing 3, 5. Then we have this special molecule. So we notice that we have a very different molecule. We have also an octane, right? If we count the carbon chain, carbon backbone, we have 8 carbons. And then we notice we have a chloride, a fluoride, and a bromide. So these are actually also branches. So the reason why they're branches, even though they don't look like branches, they're like, but the thing is we call them branches because they are not part of the carbon backbone. So what we're going to call them, so we're going to look at, start numbering it, right? So first we number it, and this has numbering that starts at 2, right? And then we also have a numbering that starts at 1. So because number 1 is the lowest number, we're going to choose, and we're going to choose a blue numbering, right? So we see first it has an octane, right? This is the backbone. We start with the backbone first. We have an octane backbone. Then we have bromide at carbon number 1. We have a fluoride at carbon number 5. We have a chloride at carbon number 6, and then we have a chloride at carbon number 7. So we have 1 bromo, 6, 7 chloro, 5 fluoro, octane. And you notice that the fluoro does not take over the O in octane, so we have 2 O's together. So fluorooctane. So you notice that, again, the way I've arranged it, even though fluoride has a smaller number, because it is alphabetically behind C, F is behind C, it will go behind it. But it has a smaller number. So we're going in alphabet. So B, C, D, E, F, right? So that's alphabetical. Then, okay, we're going to go back at IUPAC naming. We're looking at IUPAC naming again. International Union of Pure and Applied Chemistry. So this is our example that we see. So we have, look, the most important thing we want to look at first, our carbon chain. So this is going to tell us the carbon chain. And we have the first part, the oct, and this is going to tell us how many carbons are in the carbon chain. And this part is going to tell us if it's an alkane, alkene, or alkyne. Then we have the branching group, and we can tell this branching group is methyl, right? So this is a methyl branching group because, so this is an alkyl branching group, so it has a methyl. And then we notice that we have 2 methyl branches, 1, 2, at 2 different positions, and it's called dimethyl. And then here is our special one. This is the functional group, right? So again, we're going to look at the carbon chain and alkyl group names. So this is what's important. So this is this first part, right? This is going to be the same for both of them. Then we have a very different one. This is di, tri, tetra. And that is going to be the number of your branching group. So that is not the number of carbons. That is the number of the branches, of the same branches. So if you have 2 ethyl, or if you have an ethyl branch and a methyl branch, you don't do diethyl methyl because you only have 1 ethyl branch, right? And then you also have halogen branching groups, which is what we saw earlier. We have chloride, bromide, fluoride, and iodide. So that becomes chlorobromofluoroiodine. Now, these are your other branching groups. So they are different than your alkyl branching groups, right? Then, okay, we're going to look at this again. We're going to look at this one. So obviously this one, we're going to look at the longest carbon chain. It's going to be non-aine, right? First, we're going to do is we're going to identify the longest carbon chain, right? So it's not this one. This one is long. Yes, it's not the longest. This one is longer, right? We're going to look at these numbers, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. The next step in naming. So this is the first step in naming. Find the longest continuous carbon chain. And also identify the carbon functional group. So the functional group is your OL, these special things, right? So we have no functional group here. This is just regular carbon. The next step is number the longest chain, right? So earlier we saw that for this one, for this special one, for this OL, we started with the number 1 next to the OL, OH group, right? The OL, the alcohol, right? This is the OH group. We started our number 1, even though for this one, we would start numbering 1, 2, 3, 4, right? This molecule has no functional group. We are going to start with the smallest, with the number, right? That gives us the smallest branch, right? But for this one, oh, we don't care about the branch. We care about the functional group. That's why we number. So first, we're going to look for the functional with the lowest number, right? We're going to put the functional group on the side of the numbering that has the lowest number. Then we're going to look over here. This molecule, this has no functional group, so we don't care. Then we're going to have the branch that gets the lowest number possible, right? So this is our branch, which has the lowest number possible. So you can either number these ones with 4 and 6, or I can number them with 3 and 5, right? So it doesn't matter if you have 1 branch or 2 branches. We're still going to look at the first smallest branch. And then if the branch numbers are the same, you have 2 branches, and they're both starting with the branch number 3, then use the alphabetical order. With this one, we start ethyl has a higher alphabetical order than methyl. And then you look at the position and type of branches. So here are your prefixes. So you can use these prefixes. So your halogen branching groups and your alkyl branching groups. And then you determine the number of branches. So these are the type of branches. These are the number of carbons in your branch. These are the number of branches. So in this one, you notice that this one is actually wrong, because this should be 1 bromo, 6, 7 dichloro, 5 fluoro octane, right? Very important. Notice right here, we missed the di, okay? So because it has 2 chlorine, it's going to be di. So then first, again, we identify the longest continuous carbon chain. Also identify functional group. We don't have a functional group here. Then we number our chain. We number our chain with these rules. First, we want the functional group to have the lowest number. If we don't have a functional group, then the branches, if it's 1 branch or multiple branches, we want our branches to have the lowest number possible. If the numbers of the branches are the same, use alphabetical. Then we determine how many branches are they? What type of branches are they? And where are the branches? Then we put it together and we make sure that they are written in alphabetical order. So this is your 4 rules for writing IUPAC hydrocarbons. Please remember these 4 rules. Going back to our very beginning. So this is the example that we see. So we have 3-methyl-butanol. See our functional group right here. So we notice that the functional group takes precedence. It comes first. When we see a functional group, we start the numbering at the functional group, or as close to the functional group as possible, so that our functional group has the lowest number. Even though that over here, our functional group, we don't have a functional group, we actually start numbering from a different side. And this is why, because functional groups are important. Functional groups are so important that they change the way the hydrocarbon behave. They change how these hydrocarbons in air, right, how they will move next to each other and how they will stick together or how they will flow past each other. And so that's why functional groups are so important. And you can see here that ethane are functional groups. And you can even have, these are also functional groups, but we leave them in the branches. So we don't really put them at the back. So everything down here, we start putting them at the back, right? So we have our alcohol group, our ether group, our aldehyde groups, our ketone groups, our carboxylic acid group, amines, amides, and nitrites. Please ask your teachers which one you need to know, depending on your form and depending on like what you're being tested about, you'll need to know different ones. I would suggest you know alcohols, and I would also suggest you know carboxylic acids. If you need to know, you don't know what you need to know, you should know alcohols and you should know carboxylic acids. These are your most important ones. If your teacher tells you you also need other ones, please remember them as well. So they are important because they have properties that change how they interact with other atoms and molecules, and that is the important part, right? And that is all for our lesson today. You have learned how to name things. There is a practice sheet that your teachers have. Please enjoy. If you have other questions, please ask your teachers, or please ask your friends, or ask in the WhatsApp group. Thank you.